The modern federal mission operates as a tightly coupled system of cyber, physical, and artificial intelligence assets. Across military installations, intelligence operations, and deep space telemetry, the margin for error in data delivery is exactly zero. Yet the infrastructure supporting these missions still relies on dynamic, best-effort routing. Packets are fired into the network with the hope that they will find their way through, leading to chaotic collisions, severe congestion, and unpredictable latency. As GPU clusters train resource-heavy models and edge sensors generate continuous torrents of raw data, the sheer volume of information rapidly overwhelms these legacy pipes. Operational tempo requires absolute precision. Critical command data must arrive precisely on time, and adversarial attacks must be constrained long before specific threat signatures are even written. The paradox of traditional IT dashboards is that they are structurally reactive. They only observe symptoms, like packet loss or unauthorized access, after the network topology has already failed. When compute resources sit stranded waiting for data, or when anomalous lateral movement spreads through a system, operators are not experiencing a lack of bandwidth. They are experiencing a structural collapse of their network. Optimizing network performance and cyber resilience requires looking past individual packets and addressing the underlying geometry of the flows. The Tensor Networks Combined Platform, or PTCP, addresses this by implementing a deterministic topographic network overlay. Rather than reacting to fragmented packets, PTCP explicitly maps the geometry of data flows, drawing an optimal path from source to destination. This seamlessly delivers massive datasets to idle GPUs, recovering stranded compute. Congestion becomes a topological event, routing around bottlenecks before collisions occur. This moves network architecture away from unpredictable, reactive guesswork, enabling proactive routing explicitly tied to mission priorities. By explicitly mapping topology, operators dictate the geometry of the mission, securing performance and data delivery by mathematical design rather than by chance. In military and Department of Defense environments, networks operate under persistent cyber pressure and acute bandwidth scarcity. A common threat in these contested environments is a sudden flood of bulk data. An influx of raw surveillance video can easily choke a standard network, causing critical telemetry and command signals to drop. The Sarah AI mission module creates a deterministic route through the noise, shielding essential defensive data. A latency chart shows erratic video processing delays in blue, while a flat gold line tracks strictly bounded P99 metadata latency on the fast path. Because of this geometric isolation, vital radar tracks, electro-optical feeds, and weapon system controls remain fully operational regardless of the surrounding network degradation. Guaranteeing the survival of the mission's optic nerve, its metadata and control signals, ensures base resilience and operational continuity even when bulk data fails. This structural control extends directly to cybersecurity. Traditional signature-based security tools fail against novel zero-day threats because they rely on recognizing known malicious code. The Tensor Network's Quantum Geometry Engine, or TNQG, introduces a payload-blind defense mechanism that ignores content entirely. TNQG measures topology deformation. An unauthorized connection physically warps the approved geometry of the mission fabric. This lateral movement instantly registers as a structural violation, triggering quarantine. This natively enforces strict classification compartments without ever opening the heavily classified payloads. This geometry-based method identifies supply chain anomalies and protects cyber terrain by monitoring how systems behave, never waiting for an updated signature file. By utilizing topology-native signals, federal agencies contain novel threats based strictly on structural anomalies, defeating zero-day attacks before they are fully understood. Deploying this capability across the massive, heterogeneous scale of federal infrastructure requires a specific integration strategy. The platform is built on an overlay-first mandate. Agencies deploy it as a software-defined control layer without needing to abandon their existing hardware or execute costly capital replacements. The physical baseline consists of disparate agency assets: high-performance computing, industrial sensors, mission clouds, and space telemetry. The PTCP and TNQG mission control fabric drops directly over these legacy systems, providing a unified software layer. From this fabric, specialized mission modules are generated. The AI factory guarantees compute throughput, and Sarah AI protects vital sensor-to-command fast paths. Zero-day provides payload-blind cyber containment, while the ACSIO module handles governance. These modules interface directly with their respective federal authority planes, serving the specific demands of DoD, DHS, DNI, and NASA. This architecture provides a single deterministic control layer across the government, while strictly maintaining the policy, legal, and operational boundaries of each independent agency. Major national crises, like a targeted campaign against critical infrastructure, do not respect agency jurisdictions. They impact multiple federal domains simultaneously. The Department of Homeland Security utilizes this fabric to passively map IT and operational technology dependencies, ensuring that life safety communications, like 911 dispatch, maintain absolute priority over standard traffic. Crucially, it maps these industrial control networks through observation, avoiding the destructive network probing that can accidentally trip sensitive SCADA systems. Meanwhile, NASA utilizes the exact same core fabric to manage entirely different extremes of distance and data pressure. The overlay optimizes massive foundation models for Earth observation, secures narrow command pathways for orbital assets, and preserves the provenance data required for deep space autonomy. While the statutory boundaries and physical hardware differ wildly between an emergency operations center and a deep space network, both environments face data crises that share a common geometric solution. Ultimately, speed and deterministic routing mean little without human accountability. The platform exists to serve the operators making the final call. This is the function of the AC CISO module, a human-in-the-loop evidence operating system. A CISO captures the deterministic network telemetry and continuously translates it into signed, replayable operational evidence. It preserves exact provenance metadata, tracking the origin of every model, and logs comprehensive cryptographic bills of materials over the lifespan of an operation. All of this topological data is synthesized into a clear, actionable staging package, providing executive leaders with the precise evidence required to authorize a risk decision. This rigorous mathematical record can then be securely shared across interagency operations to coordinate response efforts without ever collapsing intelligence compartments. By shifting to a governed topographic overlay, federal operators move from reacting to network failures to exerting direct control over the geometry of their most critical mission paths.